class, we've been working with analyzing data by doing a linear fit. Once we graph it and we know it's a straight line, we can find the slope, find the intercept, we can find the equation. But what are we going to do if it's not linear? Here's an example. We have velocity and kinetic energy. We should know from earth science for some time in the past that kinetic energy is the energy of motion, and if the velocity goes up, the kinetic energy goes up. But is it linear? If it's linear, we can find the equation between the two, but if not, we're going to have to figure out how to deal with it. So here's some data. The velocity here is going up, okay, from 0 to 5, and the kinetic energy goes up. Now we're going to graph it. Okay, now we have to make sure we label our graphs. So down here we'll put velocity in meters per second. On the x-axis, the y-axis, we'll put kinetic energy in joules. And then we got to figure out our labels. The velocities are going up nicely, so 0. Make every two lines 1. 1, 2, 3, 4, and 5. And for our kinetic energy, we have to get up to 300. This is a little bit awkward, but I'm going to make every two lines 100. Now, I'm going to plot the points, so I go over to 1 and up to 12. Well, on the scale, one line is 50, so 12 is going to be about a quarter of the way up, so something like that. And the second one is at 2 and 48.5, so almost up to 50. 3 and 116. 4 and 195. And then 5 and 310, like that. Now, if I look at that, I could do a linear fit, but actually it looks to me a lot more obviously like this is going to be a curve. So it's going to be a curve something like this. So for a curve, we can't find the equation by finding the slope. It's not going to work. Y equals mx mx plus b does not work for our curved line. So what are we going to do? Well, if I sketch that graph that we just had, we had velocity here, kinetic energy here, and it was curved up like this. Now, that's an exponential. Something like y equals a constant times x squared, or y equals a constant times x cubed, or and so on. So what we're going to do is we're going to always manipulate our x variable. So here it says x squared. So instead of using x, I'll do x squared. So for this, instead of graphing k versus v, there should be v here, I'm going to try k versus v squared. Maybe that'll straighten it. If not, I know it's exponential. Maybe it's x to the third or x to the fourth. But I'm going to try z squared to start with. So I'm not going to graph this on my x. I'm going to make a new column for velocity squared. Now, if I'm going to square the variable, I also have to square the unit. So now I'm just going to square each of these. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. I want to make that my x variable now. Okay? I'm not going to graph this. I'm going to graph the squared one. So we have to make up our axes. Okay? I'm going to have, instead of v here, I'm going to have v squared in meters squared per second squared. The other subtlety to this is, or the other thing you have to pay attention to is, I can't use the same scale. I'm not going to 5 anymore. V squareds go up to 25. So I have to change my x scale. So I can get 25 over there to the right. I think if I do every two lines being 5, that might work reasonably well. My y-axis is going to be the same. Kinetic energy in joules. I have to go up to 310 again. So 100, 200, 300. So now I'm graphing this column in my x and this column in my y. So 0, 0 for the first point. Now my second point is at 1 and 12. So I go over to 1. 1 would be like someplace in here because this is 2.5. So 1 would be over here somewhere. And 12 would be, well, so like that. Next point is going to be 4 and 48.5. So 4 would be over here, 48.5, just below the 50 line, so something like that. My next one would be 9 and 116. 9 is almost all the way over to 10, 116, so something like that. 16 and 195. 16 is way over here. 195 is up about there. And then my last point is going to be 25 and 310. So 25 and 100, 200, 300, 310, something like that. Now it looks like a much straighter line, so I can draw my best fit straight line through there. So that, like so. Okay, now I can go back to use my technique. All right, so I'm going to pick 2 points that lie on the line. For me, it looks like this one does. Okay, that point was 25 and 310. And down here, it goes through 0, 0. So I can use that point. Now, slope is change in y over change in x. Remember, I want to always write down the equation that I'm using. And then I'm going to plug in. So my y is 310 minus 0. And remember, that was in joules. And my x's are 25 minus 0. And that's in meters squared per second squared. Okay, if I grab a calculator, I get 12.4. And my units is joules per meter squared per second squared. If you want to neaten that up a little bit, that second squared on the bottom can go up to the top, and it would be 12.4 joules second squared per meter squared. It's a little bit neater that way. Now, my intercept, I just look at the graph, it crosses at 0, 0, so my y-intercept is 0. So now, I'm going to use my y equals mx plus b, and I'm just going to substitute in where I see y, I'm going to put k, okay, because on my y-axis was k. And then equals, my slope was 12.4 joules second squared per meter squared. My x-axis, now I have to be careful, it's not b anymore. Remember, on the x-axis we had b squared, so I have to put b squared here, and then b was 0. Okay, so I don't have to add that part. So there is my equation for that now. So, in straightening, you try to figure out what the equation is and then manipulate the x variable. So, we just did this on the last page. Now you know that k varies as a function of b squared. If b doubles, k doesn't double. What's going to happen to it? Well, I have to remember to square it. So if b doubles, k doesn't double, it will be 4 times as. Now, what functions try for different shapes of graph? We just talked about if the graph looks like this, try y is x squared, or y is x cubed, or some other power. And if you try x squared and it's still curved, then try x cubed. Just keep playing around by trial and error. If the graph looks like this, that's curving the other way, that's fractional power, so y equals some constant times the square root of x, or y equals something times the cube root of x. Okay, try something like that to straighten it. And then the last thing is, if it goes down like this, it's inverse, so it's y equals c over x, okay, or I'm going to graph it like this, y equals constant times 1 over x. And then, or, it might be an inverse squared, which would be y equals c over x squared, y is c times 1 over x squared. So whatever's happened to the x variable, that's what you're going to graph. So in this one, you might try graphing y versus x squared, or y versus x cubed. In this one, y versus the square root of x. Okay. In this one, y versus 1 over x. And see if that makes it straight.